Okay, today I wanted to do a quick mini lecture over periodic trends. Two of the specific ones that we need to know in our learning objectives for for intro to chemistry is going to be atomic radius. We're going to define what that is and how that trends on our periodic table, and electronegativity, what that means and how that trends. But we're going to start here with atomic radius. What I have here is a very quickly drawn periodic table. Notice we have our left side of the periodic table. At this point, we should know what exists in this area. And this area, again, remember, is metals. Specifically, alkali metals and alkali earth metals, specifically. And then, notice I have an X over the middle of the periodic table. We're not going to be so concerned with the middle of the periodic table today. The transition metals, not so much when it comes to these trends. We're actually going to kind of leave them out of this. This area of the periodic table, which we know is a mixture of metals and nonmetals, but the line, the metalloids line, gives us a little insight into the difference, again, between metals and nonmetals. So today we're going to be focusing on specifically these metals and these nonmetals as it pertains to trends. Other than these metals and these nonmetals, you won't necessarily see a lot of comparison questions about any of the trends. It's generally a function of these two areas, again, of the periodic table. So let's talk a little bit about what is atomic radius. When we talk about atomic radius, we can define the atomic radius very simply as a distance from the nucleus, the center of the atom where the protons and neutrons exist, to the edge of the electron cloud. Now this is where I wanted to bring in what we have been studying and why the physical doesn't necessarily represent what we draw pictorially in some of our situations, particularly the Bohr model. So here I have a Bohr model type diagram drawn. I have a nucleus with a single proton, and I have a single electron. If I was to give you this as a question, you would tell me that this represents what atom on our periodic table, and hopefully you would realize that this represents hydrogen. This will be a ground state hydrogen. One proton, one electron. Okay? And we draw our rings, like our orbits, as our energy levels, and we draw a dot for an electron. Now, if we thought about this in more of a three-dimensional situation, then we actually end up seeing a sphere where we still end up with a nucleus in the middle, but we end up realizing that since electrons are constantly in motion, they are constantly moving, we think about them as far as where could we find an electron? Where could we find one? And where we could find one is a three-dimensional space. It is a volume. And within that volume, we expect to find our one electron moving around acting crazy. And that I wanted to depict as a red dot just to make it easier. So the electron can be anywhere in this volume. And let's just say it's right there for now. What the atomic radius, and I'll actually draw this as black because I'm going to use the red for another thing. What we describe as the atomic radius is this distance here from the nucleus to the edge of the volume that the electron cloud makes. And this is R. We should be familiar with the radius. Remember, radius is half of a diameter. So I'm trying to show you pictorially what it means. Now, more importantly, why do we care about it and how does it trend on our periodic table? Notice for the atomic radius, and I'm going to do this in green just to keep it color coded. Notice for the atomic radius, The direction that the atomic radius increases for our particular areas of the periodic table that we're worried about is that it increases going from right to left, so going towards the left side of the periodic table, and it increases as we go down. So the trend is right to left, and up to down. And this is the trend direction of increase. Notice where my arrow is pointing is the direction of increase. And better explained as left and down for atomic radius. Now let's talk about the why. Why is it that it increases in that direction? Well, what we should also recognize is that if we compare hydrogen, let's say, to sodium, if you will, what we know about sodium is that sodium has 11 protons in it. It has a nucleus with 11 protons. So that's 11 positive charges attracting these electrons. If we look at the Bohr model, we notice that ground state sodium should have 11 electrons like such, right? And let me write this in. This is hydrogen. This is sodium. So the point is, why do they increase as we go down a column, down a period? And it has to do with the addition of addition of protons, The reason that the atomic radius increases is because the addition of protons to the nucleus means that we are adding energy levels to the electrons. Notice we only have one energy level here. We have 3 energy levels here. What happens is that the inside electrons, specifically these two on the first and the second energy level, they do what is known as shield, or they cover up the proton's positive charge. They cover up the proton's positive charge, which means that on an actual situation where we have 11 protons, the last electron, or the outermost electrons, can get further away from the nucleus because they don't feel the attraction as strongly. That's the best way to put it. They don't feel the attraction as strong. So what ends up happening is that we end up with a situation where the atomic radius is now much, much larger from the nucleus to the outermost part of the electron cloud. The volume in which you can find the electron is much greater because the pull on the electron is still 1-to-1. Notice that. We got a 1-to-1 ratio, but the pull on the electrons that are the furthest away is lighter. They're not pulling as hard. The one that I like to make is it's harder to interest the individual that lives far away from you. One that's really close, you can talk to them, you see them a lot, they're closer to you, you can interact with them. The one that's far away ends up kind of doing their own thing. Same thing here. You see that atomic radius increases as we go down. Atomic radius increases as we go down. All right, let's talk a little bit about why it decreases as we go across. So it increases as we go down. Let's talk about a scenario when we go left to right. Let's look at the example of fluorine and lithium. So let's look at lithium. Lithium has 3 protons. and 3 electrons, excuse me. I'm drawing fluorine. And fluorine has 7 protons and 7 electrons. Okay, so here is an example of lithium. So with lithium, we see 3 electrons, we see 3 protons, we see only 1 energy level between the nucleus and the outermost electron. And in that exact same energy level, 1s and 2, remember, lithium and fluorine are in the same row. So we're looking at in the same row. That's why we're looking at this tree. In the same row, lithium and fluorine. The only thing is different is fluorine has more protons and more electrons, but we're putting electrons in the same energy level. We're putting them in the same energy level. And that energy level is only the second one. So it's similar distance away. So the attraction between the protons in fluorine and the electrons on the outermost energy level are a little bit stronger. You know why? Because fluorine has more protons, more charge. So the more charge increases the strength, and by increasing the strength, pulls electrons in closer. Lithium has 2 electrons on one electron, on the outside, but that electron is only really attracted by the force of 3. But as you get closer and closer to the noble gases, as you get closer and closer to fulfillment of octet, fluorine is pulling electrons in closer. So how does that impact our trend? How do we show that? The actual for lithium with 3 protons is larger than the actual for fluorine. We have actually a larger atomic radius for lithium because of less protons. So this radius is much smaller than this one. So the increase occurs as we go from fluorine, which is here, to lithium, which is here. Increase to the left, increase going down. So that is the trend and the Y for atomic radius. All right, let's take a look at electronegativity. So electronegativity is how strongly an atom pulls electrons when bonded. Very, very simply put, if 2 atoms are bonded to each other, electronegativity will tell us which one is hogging the electron, right? Which one is holding on to most of the electron density. And we've talked about this in the context a little bit of shape and polarity, and there will be a subsequent video that talks about that. But electronegativity is what gives us and leads rise to polarity. All right, so let's look at the trend of electronegativity on our periodic table. Notice that we're working in red now for electronegativity, and we see that the electronegativity of an element increases as you go up the periodic table and to the right. the exact opposite trend of atomic radius. They are opposite trends. Increase in electronegativity goes up and to the right. And let's talk a little bit about the why. And it comes all back to atomic structure. Atomic structure is what gives us rise to all the periodic trends. Let's look at lithium and fluorine again. Let's look at sodium and chlorine. Let's look at sodium and chlorine to use two different examples. So if we look at sodium, sodium has 11 protons. It has 11 electrons. And it is in this metal section area of our periodic table. Okay, if we look at chlorine, we have 17 protons. And it looks something like this if we're talking about Bohr models. Okay, so if we look in the same row, let's look in the same row. Let's look at our trend in the same row. Then chlorine is more electronegative than sodium, and it has to do with octet. It has to do with lowering our energy because, again, everybody wants to fulfill octet. They want to have a full energy level. We want to have 8. Notice that to get sodium to 8, we will lose this electron and create our sodium ion, Na+. So sodium is very friendly when it comes to giving up of electrons, right? Giving up of electrons. Therefore, from a electronegativity standpoint, it's never going to hold and pull and be greedy with electrons if it wants to give one up. Metals, in general, are always going to be considered very, very, very low electronegativity. And notice that is the case in our trend. Metals on the left side, low in electronegativity. Now, if we go to the right side, we see our nonmetals where our chlorine is. Chlorine wants to fill in this last spot to get the octet. They want to fill it in really badly, really bad. So with chlorine able to fill this in, what does it want to do? It's definitely greedy. It doesn't want to give one up. It's almost got a complete set. So chlorine is going to be greedy with electrons when we're talking about bonding scenarios. So if we had to compare two, we would say chlorine has a higher electronegativity than sodium because of the trend. Because of the trend. Now, if we wanted to look at the trend up and down, let's take a look at the trend up and down, and let's go with potassium. So potassium and sodium are in the same column. And we say that the increase in electronegativity is from bottom to top. From bottom to top. Which means that Na should have a higher electronegativity than K. Again, this is an entirely different scenario. Before we had chlorine. Now we have potassium, K. K has a lower electronegativity because of what we just talked about previously, the shielding. The shielding. More and more, and K also doesn't have 17 protons. K has 19 protons. The more energy levels you pack on top of the nucleus, the less positive force is felt on the outside. So that last electron is really, really ready to go. It's even easier to pull away. Therefore, we know potassium doesn't have that strong of a pull. Doesn't have that strong of a pull. So how does electronegativity manifest itself physically, right? Being able to compare them is one thing. How does it manifest itself physically and bring it to interest in all of the topics that we're talking about? Well, that's where bonding comes into play. if we take a look at two highly different elements, and we looked at the Lewis structure for hydrogen fluoride, we know that electronegativity increases as we go up and to the right. And if we look at a periodic table, we see that fluorine is the furthest up and to the right in the nonmetals. Somebody might ask, well, what about that last column? Good you brought that up. That last column is noble gases. Noble gases don't do any bonding, so we leave them out of this discussion. That's why I have them X'd out. And again, the transition metals, similar as atomic radius, we leave them out of this discussion. But noble gases don't bond. We don't have to worry about them as far as electronegativity. So fluorine is the highest electronegative atom on the periodic table. And in a second, I'm going to show you the Pauling scale. But fluorine means that it's greedy with electrons. The bonding electrons associated in this bond here, covalent bond, force the electron density to choose to hang around fluorine more. The probability of finding the bonding electrons associated here are going to be found around fluorine, and therefore we end up with a partial negative charge over here and a partial positive over here, right? And that is due to electronegativity difference. So this is how it manifests itself. Again, check the videos on polarity and molecular geometry, and those videos are going to utilize these trends to show you how they impact chemicals' polarity and their behavior. Also, really quickly, I wanted to show an image of the Pauling scale. And the Pauling scale is not something that we necessarily use in our class, but I wanted to just give you a generic look at kind of how and why it matters. If we look at these, and again, these are relative values, they don't necessarily have a unit. Notice that as you move to the right, these numbers increase, and as you move down, they decrease. And notice that our metals are all shown generally in green, and they have lower electronegativities usually than our nonmetals. And these nonmetals up here and here are going to be your more electronegative atoms when we're dealing with covalent compounds. Remember, covalent compounds only involve these yellow ones plus our hydrogen over here.